short week, so maybe people. Okay. Okay. All right. So what I want to discuss today is actually some kind of very recent thought I had with lots of literature, some new literature for me, but actually old literature that I found. And so actually what I will present you is much more questions than answers. And my purpose is really to try to understand, okay, just to find back the definition. What does it mean, the emergence of life? What means self-organization? What means all the stuff that you are talking about generally, and just to try to understand what does it mean actually to try to understand how life emerged. So yes, what are the good questions? So roughly my three parts was just to try what is the emergence of life, what means this replication of information, and what is self-organization. And roughly these three questions that I try to better understand. So what about emergence of life? So so my approach is with the approach of a chemist, and so what are the fundamental properties of a biochemical system? And a biochemical systems, a biochemical reaction network, there is this fundamental point, that is there is existence of a coding system, that is this network, we have some very direct relationship between some molecules and other molecules, that is RNA or DNA and protein. You will have a very precise relationship between these two systems, that is this coding system. There is the generation of highly selective catalysts, that is proteins, so that we are able in this kind of system to perform very precise chemical reactions and not others. And globally this network is extremely organized. That is, we have very precise pathways, and all this network is really based on very central building blocks, and we have very complex molecules, but all these complex molecules, or most of these complex molecules, are really built upon very specific building blocks. And so roughly this can be represented like that. We have coding systems. These coding systems allow the formation of very specific enzymes that are very selective, and this high selectivity allows a structure of the whole network, and it's inside this very structured reaction network that the coding ability is possible. And the problem is that we have this chicken and egg problem there, and if we try to link this with the different problem, the different approaches that can be seen in the literature, is that yes, the RNA first theory, that is okay, first we have coding and then everything could emerge. Yes, the protein first, that people say okay, but no, first we need some very efficient catalyst so that it works, and so it starts from selectivity and then etc. And you have the metabolism first approach. This is not okay, but first we need something that is quite organized, and then etc. etc. And so this is really the circular problem. And so I think that the question is, well, what is the center actually of that? How we can have really the emergence of this? Because if we just think of this chicken and egg problem, we do not think of whether some chicken Eve that appears magically and then generates the first egg, or some first eggs that appear from nothing. No, we really have to understand that, okay, that there was something before. And so the idea is much more to try to understand what is the common origin of these systems, or every element or interdependence. Yes. So the question is really what is the common origin. And so in this scope that I try to discuss in the emergence of proto-metabolism. That is, well, to try to find a system where you can observe this self-organization. And so how we can start from something that do not have all these properties, and what is the pathway where you have all these very fundamental points that can be observed. So, replication of information. Why? Speaking of that. There are a very important point. So I say that is in this coding system we have information. So what means having information? So what I try to represent there is, okay, in gray, just imagine it's all the possible, in the space of all possible molecules that can possibly make. If, for example, if you imagine that this is a space of possible proteins, it's in this space you have all the possible codings, etc. And if you look at, for example, biochemical systems, you will have only a very specific phase space, a very specific area that is represented. You have only few molecules in all the possible. This would represent in a way all the combinatorial possibilities. And actually it's impossible, of course, to represent the whole space. And more than that, knowledge systems, you only have very specific molecules that are represented. But if you just, for example, start for a system with only specific RNA molecules and you just leave it as is, what happens? You will sort of lose information. That is, if you do not have a very precise coding system, you won't reproduce exactly the same molecules. So the molecules will degrade, and if you synthesize other one, well, you won't synthesize exactly the same one. And theoretically, this should go to the what I can call the thermodynamic net. If you take a chemical system, whatever you do, it will have only one stable state, that is the thermodynamic equilibrium. So it means that if you do nothing, theoretically, all the possible states should be reached, just depending on their relative energy. Of course, there is a problem of this combinatorial space is very large, so maybe it's not possible to have all the molecules in the same time. But it means that sometimes you will have only one subset in this phase space, but after another time this subset may be totally different. You have the molecules as long as the time is progressing, we will have some arbitrary random molecules that may be built, and you probably won't have any relationship between all these. So this is really a totally random state that is, okay, this is the equilibrium. But if we look what is doing life, is that actually we have a very, these coding systems really keep the information. And what means that we keep the information is that the system remains centered on a very specific area in all the possible combinations. And so it's really a conservation if we always stay exactly the same, or we can do something a little more complex, that it can have the evolution, that is this area may displace, we do not have exactly the same, but some molecules that are slightly different, some may disappear, some may appear, etc., etc. But what is very important is that we are keeping the system in a very specific area. And so if we try to think of what we have there, what we are describing there, is that what we want to build, if you want to build live. And when we want to build this very precise informative system, is that we want to reduce and maintain the system in a very specific zone on all these possibilities, and we want that the zone do not correspond to the energetic minimum. And so what that corresponds to is exactly what we observe in bifurcation system, in bifurcation chemical system. Is that we start with what we would like. This is life, but what we like with self-organization, we start from this random state, and we want the system to collapse on a very specific area. So what we want to find, if we want to understand what is life, is we want to understand the mechanism, and we can have all the possibilities, and we want the system to collapse somewhere. But of course this will probably depend on the history of the system. If that is, maybe this is good, but this is not good for itself. It's not, maybe there is another area that is also very good, that can maintain itself, but okay, we are in this place and not somewhere else. So it's really exactly what we observe in bifurcation system. And moreover, actually, it is necessary, if we want to maintain that, to consume energy, because it is not a thermodynamic state. So we need an active system that allows to evolve in one direction rather than another, and this evolution can just be some kind of choice, sort of, that is some kind of bifurcation. And if we want this, maintaining this, we need some continuously consumption of energy. And so we see that there we have all the we already need this all these 3-point data type, because this encoding system, actually, what is it? Well, it's just maintaining the system in a very specific place. It's not, we understand there that maybe we don't need a very precise coding system that is really from 1 second we'll synthesize exactly one protein, etc., etc., and one RNA must be reproduced exactly the same as its parent, etc., etc. What we need is just to have a system that maintains itself in the same space. So here we have some kind of information conservation rather than coding, and for that it means that, well, molecules that are in one zone must favor the formation of molecules that are either exactly the same or close to themselves. So it means that we need also some kind of selectivity, and for all that we need a very organized system, a system that consumes energy. So we need also this metabolism-like system. So we see that we can have all these 3 points, but maybe we're beginning to collapse them in one single point. Okay, so what really is beyond there is really this self-organization. But what does mean this self-organization? So this is typically, actually, so the questions about developed by Bennett, and so it's very early. So there is an article in Foundation of Physics in '86, but there are very old articles that start from the very early '80s, or maybe at the end of the '70s, and is really defining, if you want to organize what is the self-organization, well, it's really defining, okay, but what is complexity? And it's not so easy to understand what is complexity. So it's just defining that the complexity is just the number of minimum steps that you would have to reach this state from a random one. And this really, this is interesting because it really goes to the conception that I can show you from the beginning, that we want to reach a non-random state from a random one. And what is important is that we have to start from a state with no information. It's when we're reducing the system toward a very specific area, it really means that we are creating information. The information is that, okay, we are there and not there. So here, so what we really want to do is really to create information. And so, in this kind of system, there can be lots of solutions. There are only two possibilities. Either it is possible to generate with high probability such a non-trivial state with a finite number of steps, and then we have a true self-organized system. And in this case, we will be able to describe life as a process, as a universal property, because it means that it is at least theoretically possible to start from a state that is totally random, and with very simple rules. We do not input nothing in the machine, but with very simple rules, it is possible to evolve in one very specific and interesting state, and not in the other. Or maybe, well, I mean that this may leave the system in one place and not in the other. And the other possibility is that maybe this is not possible. Is that if you want to reach a very organized system, maybe there is some irreducible complexity that you can't avoid. That is, okay, life is just an accident. If you have, generally you have nothing, but if by some very improbable chance you have the specific state that appears, then life can appear. And this is really the approach that when people are describing the original life just as an event, an improbable event, but okay, we are there, so this event had to appear. And then it would mean that maybe we are alone in the universe. But of course, I think that yes, we have to assume that the possibility of a true self-organization of theoretical system, and take this because it's the only possible, the only falsifiable hypothesis, the only scientific hypothesis that we can make. We can only suppose that it's possible to have this self-organization from random, to have this self-organization from random to a non-random state, and test this hypothesis. And this is actually exactly what Bennett and all the people working in this ground are doing, but on the basis of very theoretical cellular automaton, etc., just to try to build systems that are self-organizing. But we are self-organizing from random state. Typically, is giving the example of this game of life. It's game of life. The rules are very simple, and they can make very interesting stuff. But the problem of this is that you always need some already input information in these systems. Theoretically, you can do very precise computations, and you can build some Turing-complete computations on the basis of the game of life. But as long as you input the good initial conditions. So the game of life is not a good answer. It's not a good answer for self-organization, because if you start from a random state in the game of life, the system will remain random with just specific organization, but nothing interesting actually.
So the fact that you say it should be a rare event has to do with the fact that you need a certain minimal amount of molecules that happen to provide information and that constitute a minimal metabolic cycle to start with. So maybe start from zero, you're saying.
Yeah, well, I mean, really that it's really a specific event. If this was true, it would mean that maybe we would require even more, maybe a very precise protein and not, a very precise peptide that will be able to, I don't know, maybe or some very improbable event. I don't know what it can be. Maybe we need this compound to appear exactly in the same moment at the same time, and then maybe it can start, and we can't explain anything without that. But of course, this is intellectually not very, it's quite disturbing. That to mean that, it means that we're really there about pure chance.
I mean, in terms of bifurcation theory, that really just means that they have a bifurcation, so-called finite amplitude bifurcation. So that means you cannot really start from zero, but you have to be lucky enough to be close enough to a state where you...
Yeah, but with this bifurcation, it's much more to see that, well, for really a random set, is that you have some attractors in front of you, and that whatever you do, well, the system must evolve in this direction or this direction, etc., etc. And if the system process in this direction, then in etc., etc., you may have a continuous process, and that as long as you start from the good conditions, the system can only go there. But maybe these conditions are so narrow that you really require some very specific state, then life can be only seen just an improbable event. But if these conditions are so narrow, it's that you can't test them. It's not really a scientific hypothesis. The scientific hypothesis is really, okay, let's try to see that we will assume that from a very random state we can have this self-organization and really try to test it. I think it's really the hypothesis, and I think that we have elements to say that tends to say that it is possible really to have this self-organization, because we know all these very simple systems that are generating this autocatalysis. We have this non-trivial self-organization. Okay. 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 That's yeah.
I'm sorry.
No problem. Okay. It's okay, but you see what I mean when I with this very two difference actually in vision of how life can be, and I think that and this is really I really try to translate this maybe just in terms of origin of life. Bennett is really defining this in a very precise way. But the problem is, okay, it's really building that on the basis of Turing machines or cellular automaton, etc. And when you're studying the evolution of this artificial life, it's really trying to make the difference between the systems that are actually, I think he called these systems ambitious. That means you have this cellular automata, you give them just a random state. But these cellular automata are able to transform this random state in a structural one. And so it gives this very simple example of cellular automata that is very simple actually. There's some...
Yes.
Yeah, and what is interesting is, so you have this ambitious system where you really have self-organization from nothing. This one typically is a game of life. If you need some very interesting to reach non-trivial state, you need to start from already non-trivial state. And that is, you don't really have creation of information, but the information is the one that is building the initial state that puts the information in. And so the idea is that if you want to really understand how life originates, well, we need that, because there is no way that, when you started, there was no information. So we will have to try to find what is the pathway to be able to start from a very random state to a non-random state. And so for the very simple example he's giving is, it's a very simple game. That is, if you start, you have some wet machines, some right machines and left machines, and the right always going to the right, the left always to the left. Okay, so you start there, and when they are meeting, you have 50% chance that the one hits the other, and so maybe, okay, if the right win, okay, this will survive that, etc. And in this very simple machine, if whatever the initial state you start, at the end, okay, so you will observe this kind of evolutions, etc. But at the end, the machines are all going to one direction or to the other. And it's interesting because in this very simple, well, actually you don't know if this can really be called a true self-organization because it's very, very simple. But it's interesting because this is actually exactly the problem of emergence of sort of homocausality. And
it is certainly an example of self-organization, but it doesn't allow you to go any further from there.
No, of course. That's why it's just giving. It's a very simple illustration of what can be some true self-organization. Actually, that you don't need some specific initial state to reach. And that's what is important. Mm-hmm. Okay, and so what? I wanted just to go a little further, and okay, let's try to understand this self-organization in this terms of this bifurcation system. So if we take this APED model, that is okay, we just have a system with lots of polymerization, etc. What is interesting in this model is that, well, as long as you input energy, you have the self-organization of the system, so the reaction network is no more random, but it becomes organized around some specific chemical loops, and these chemical loops actually generate autocatalysis, so we have also the emergence of some selectivity, and this leads to bifurcation. And the bifurcation, so it means that it leads to some kind of information conservation. So okay, this is the first. Oh, I'm not doing it. So yeah, this is the kind of mechanism of that can the kind of fight mechanism that can emerge, and so this is typically the kind of evolution of rapid systems that can be computed, taking into account complete polymerization. So this is our very new results.
What is EPET?
Yes. Okay, it's right that I was talking quite fast. Okay. So in this system, it's way that we have some L and D monomers. We activate them, so we input energy. We have polymerization. So this is the activation, this is polymerization, and okay, we can generate whatever, etc. We can generate everything. So this is computed with a stochastic algorithm. So we're starting here from just 5,000 monomers. So we have some epimerizations. This, for example, the DDL can be transformed in DDD, etc. And we have the hydrolysis by the depolymerization back to the amino acid.
So how much of mixed states do you allow here?
So this is a representation of all the possible molecules that were represented. So I have that, this system, we have from continuously this activation, polymerization, depolymerization,
but you don't see the order. I mean, if you are, for example, at the corner 1, 1,
so
it could be an DL and an LD.
So
you don't distinguish between them.
Yeah, okay. Here what we can see is that we have this number one, this is about 2,000 molecules that have only one D. This is the D amino acid, this is the L amino acid. So this is LL, this is LD plus DL. I just represented it like that just to have a simple representation.
Yeah.
And this is DD, this is LLL, this is LLD plus LDL.
So in other words, you have all the mixed states, but they are
subdivided
into one block.
Yeah, I didn't separate this one because it was just more easy to separate. Mm-hmm. And so what we can see in this kind of system, so this is very close to the equilibrium. We just have this mixture of states, and actually it's really a combinatorial distribution. Mm-hmm. We have all the possible, well, not all the possible, because as long as they are too long, we do not have any enough matter to represent them. But okay, we have this exponential decay of this exponential distribution of all the compounds. And if we input enough energy in this system, we can have the bifurcation. And so the system, the site is collapsing in only one zone. And we go a little further actually in length. So actually, what is end? Okay, we have the reduction there, but the reduction may have been there. So actually, what the bifurcation is doing, well, it's roughly what I was showing to you before, is that we have this, okay, so the phase space of all possibilities, of all possible combinations, something like that, and at the beginning, we have some fuzzy representation there, that is, we have potentially everything there. And when we put energy, actually what we have is that in this phase space, yeah, the system is collapsing in only one zone or in the other. Of course, this is very simple, and because the phase space is very simple to represent, we only have two kinds of monomers. And so the question at this point is, would it be possible to observe this kind of collapse of the systems with much more complex systems? If we start with lots of different proteins, lots of different amino acids, for example, is it possible to imagine to have the system that will collapse on a very specific zone, that is with much more specific amino acids or very specific sequence? Is it possible to have that, or is it not possible? Or what do we need to have that? Do we need some kind of coding with RNA to really have that, or is it possible without it? Well, there are lots of questions there, but I think that it's, in very general terms, if we want to understand what is the self-organization of the chemical systems, we have to think in terms of this evolution of the system collapsing in a very specific zone of the phase space of all possible states. And if you want to understand that, well, it really means that we have to understand what are the possible bifurcation systems that can be built. And so it's really in terms of self-organization of reaction network. It's really that we have this chemical network, we input energy, and because we input energy, we will generate cycles and autocatalysis. And it's only at this moment that we will have the possibility to have this fight mechanism. And if you have this fight mechanism, we will have this bifurcation that are possible. And that one moment we have these bifurcations, it means that we can collapse some pathways and increase some other one. And then we will be able just to have the system that evolve in one direction and not into the other. And at the moment that we have this kind of choices, it means that we are really creating information from nothing. Of course, it's very primitive information, but it's really, well, I think the only solution that we can imagine to really understand how we can go from a non-trivial state, from a trivial state to a non-trivial one. And so, perhaps the conclusion with this will be to try to understand what is this evolution of complexity. So, we need to understand what are these bifurcation mechanisms that leads to this extension of some pathway and to favor the persistence of others. And so roughly the idea that it's what we are describing there is really an evolution of the nature of the complexity. Because if you look at the very primitive, the prebiotic chemical systems, they're actually already quite complex. You have lots of chemical compounds, but you have no selectivity. You have a very random state. If you have different kinds of amino acids, but you also have maybe some kind of primitive sugars, etc., you won't have selectivity. You won't have only nice chains of amino acids just polymerizing themselves, sugars doing themselves. You will really have the network will be very untangled. Everything can be linked to everything, and you have no structure. And so what that it was would call this horizontal complexity, and this can be represented there. And we are evolving toward some kind of vertical complexity. It means that actually we are reducing the complexity of the building blocks. We have only very few simple building blocks, some elemental molecules. But then the molecule is built upon these building blocks to make maybe very long chains, etc. And then we have another kind of complexity that is emerging. And this is what can be worked in that. From this kind of complexity, we are reducing the system on one state, but that allows to go much further. And so actually each time that you are collapsing on one zone, it's just actually opening other possibilities for further complexification and organization of the system. And so it may be interesting to read, rather than trying to see some complexity emerging from nowhere, maybe it's just to see how the complexity is reshaping differently. And this is really, really fits in this vision of analyzing the chemical networks and to see the dynamic of these chemical networks in terms of evolution of the topology of the network, and to try to understand how the networks, the dynamic inside the network implies some feedback on the network itself that force him to reshape and to be much and more organized, and so that we have this change of topology from random network to scale-free network, etc. And so, yeah, roughly is that we are describing this gap, and it's what everyone is trying to do in original, to try to understand what is the gap between these probiotic systems and the first real reproductive systems. And at the moment, no one knows what's between. And so it would be interesting to try to describe this as this evolutive proto-metabolism, some very non-structured network toward very structured network. And in this gap, so we are not anymore talking about real template replicators as we have in life with RNA, etc., etc. But it's really this network replicators of similar reaction cycles. It's really that rather than this exact, we have these exact molecules, and so we are building these almost exact molecules. It's really that we are in this phase space, and so we are reducing there, and so because of the history, molecules are much more around this space. And so they are reproducing, they are just autocatalytic, so they are just reproducing similar molecules, but just because it's inside the network, rather than real template. And so, okay, I think that it's almost all I had to say. I think it's the end. Yeah. So, okay. So here all all the ideas I try to develop, I try to making link between different works and different approaches that are in this field. So now let's discuss about it and see what can be done on this basis.
Thank you, first of all, for stimulating us. So, I mean, in order to make the example with this APAD model, the thing that one doesn't see from that is it is really too simple in the sense that there's really only two states in the end possible.
Yes, of course.
Either everything right or everything left.
Actually,
so we need something which we need a somewhat better example, I think. In the near future.
Well, I think it's actually it's at the same time the best and worst example.
Yeah, right.
It's the best example because it's very simple.
Course,
well, maybe it's just.
But isn't it?
Yeah.
So I think what is at the heart of it is, I mean, at some point we need some data, so to speak. We need data which tell us how certain molecules, if we have those, how they will react with each other to produce something else.
Yeah.
We need either second order reactions or even to some extent third order reactions. We need simply data which tell us that from this big pool of molecules that you start with, what are the probabilities of getting from with two or three of such molecules to something else. And these will be non-trivial data, of course. We simply don't know those, and nobody will be able to measure those. But maybe one can, at least get the ball rolling, assume some kind of a random reaction matrix for that.
Yeah, but this is typically the work of Kaufman. He studied that towards the end of the 80s, actually, I think.
Right, and what happens then?
Well, I think that all this work are really showing that the system are organizing around some cycles. Well, not all the systems, but in good starting conditions, the system are organizing in autocatalytic cycles,
so how many
etc.
attractors do you have in such systems?
I don't know how much the details of that actually, but well, I think that the system organizing around autocatalytic cycles, that's mainly what is observed. It's that, but okay. But the problem is, so the problem with these systems, there are critics. If there are some critics about it, because maybe they are not chemical enough. So I think that maybe just showing that is some different way. Of course, this is much more simple, but much more chemical.
But what I mean is, it's what we want is the same thing. It's just
So, but the problem is, as long as you want to
more complex.
Yes, it's more complex,
I mean,
and we have to.
Here you have the number of building blocks that you work with is on the order of 8. Or something.
I really see your point, and maybe we should try to.
Right?
But the problem is after that. Well, we just have to see. There are lots of parameters that we can play with, so it depends on what we want to show.
I mean, I think it would be nice to see that you can have multiple attractors, and that you can go step by step through at least a few of them, not just from one to another one, but to have at least 3 or maybe 5. And attractor number 4, then you go to 2, and then you go to 5.
With this kind of polymerization, depolymization, to have some. I think there are maybe lots of interesting stuff, but it's not a small stuff to be done because there are lots of parameters to play with and lots of stuff. But okay, of course, it would be interesting to see
the mathematical framework would simply be. Working this random reaction matrix, or not exactly random, but at least rather complex and big reaction matrices, and maybe it's good enough to construct them randomly. Then study that system. So then one has a mathematical framework, and this one would be one example of that.
But
really
I think that it will really go close to the system of Kaufman. Kaufman is also some system of polymerization of monomers, and we have to check that. I think that the idea is good, but it's really going close to what has already been done, actually.
Yeah, but what else could be done? I mean, was that not useful then in the end?
Yeah. Okay. The problem of the Kaufman system is that you have lots of non-trivial catalysis that are imposed, and that you arbitrarily decide on just a random way that, for example, these molecules will be able to catalyze the formation of this one, etc., etc. And it's really what is shaping the system. And the question is, okay, so if it's random, it seems to work in some condition, and so what? Well, the point is, if you really want to go to real chemical systems, is that how do you predict what molecules will catalyze what. Either it's random, and so people say, okay, but it's very theoretical. This is not chemical. Either it's not.
No, but, yes, of course. Yeah, but in the end, these would be data, of course.
Yeah.
That you need to determine.
But what I really think is that the very theoretical model are showing that it's really theoretically possible to have the self-organization of this kind of system. But then the point is, how now we must bring these systems closer to chemical systems. And this is really the point. And this is really not easy, because how do you predict and show the reactivity in a non-random way of all these possible molecules? Do you see the point?
I mean, I think you're basically saying you are upset by just inventing data. Is that what you're upset about?
But I think it's the major critique of the work of Kaufman is that, okay, but it's just computer stuff. So how can we make that not so computer and more chemical?
Okay, sure. I mean, but if the framework is the right one, then the problem is really just to obtain those data. So in that case, one has to come up with the experimental strategy that allows us to determine all those possible reactions.
This is not, no, this, yeah. No, I don't know.
Is that right? I mean, these are obviously quantum chemical calculations. If you wanted to calculate the reaction probabilities between certain molecules.
Well, I was maybe thinking more, is it possible to just to try to well, how could we sort of determine what can be the catalytic properties of some peptides only on the basis of very simple rules?
Well, that's even worse, because I mean, so the point is, you have a certain word, a word being a molecule, a polymer, of course, and you just have a huge amount of possibilities of constructing words, of course, and you need to do something with these words, and what we can do with these words is in principle, it can be calculated. But we won't be able in practice to do that.
What I would better see, maybe rather than deciding that we have only just random catalytic activity, what would be interesting, maybe just okay, we have this polymerization with, I don't know, 3, 4, 5 possible type of monomers, etc. And we try to decide just to pick up, I don't know, 10 random specific sequence, and say that, okay, these 10 possible sequence may each one have some specific catalytic activity.
To do what?
To activate the formation of other compounds, but only a very similar simple state. And is it sufficient to switch the system in one direction and rather than in the other? But I don't know. There are lots of stuff that can be done. Actually, there are lots of possible parameters, and the problem is that we really have to be more general possible. It's not easy.
I mean, I think this will all still fall in the same framework of reactions. I mean, you're talking about very simple rules. But of course, the very simple rules would be a certain set of reaction matrices too. Absolutely, just together with the corresponding rate coefficients, of course. And if you're talking about a very simple system, then this would be relatively sparse. These matrices. And if that's good, then that's good. But but there's a natural pathway to make it more extended. Much more extended.
Well, okay, yes, it just comes down to...
And I would really be happy to see at least the transition via multiple attractors, or multiple, they're not really perhaps attractors, they are saddle points maybe, or something like that, semi-stable points, where you can reside for a certain time, and then of course some of them will continue going towards other points. And this I would like to see, and at the moment we don't see that, because it's really too simple.
Yeah. So,
but it's quite possible that with this mathematical framework.
But actually, the point is, okay, maybe the point is even more simple. Is that if we have lots of different kind of monomers in different proportions, and what? Okay, we have these matrices of all possible rates, or possible additional catalysis, and the question is, what are the possible matrices that are required if you want to observe possible bifurcation and reduction and evolution of the system in one direction rather than in the other? The problem is that the space of search is huge, so how can we choose what we will test? And this is really the problem, actually.
I agree.
Okay. And the fact is, okay. And either we are reducing too much the system, and so it becomes quite trivial. Either it's too large, and then it's very huge space of search. So,
yeah.
Did you include have you read the new book of Stuart Kaufman? I haven't.
Oh no, I didn't.
No. So when you talk about
okay,
Kaufman,
no.
you talk about the old, and then
but I saw a talk of, I saw a talk of him maybe 2 years ago.
Okay, so my question I can pose. I mean, in these approaches, we have usually a safe mathematics, and then we try to relate it to a chemistry which totally depends on catalytic properties, which we do not understand. There is no good theory.
Exactly.
Every year in the Nobel speeches, the prizes are given for catalysis, but it's not understood. So here we are in between, right? And now if Stuart Kaufman, who thinks I know, develops the whole Poincaré and what follows beauties of mathematics in usually explicit time frame and the fluctuations, there are lots of things to discuss, and I take him serious for the mathematics, so I ask him questions for the mathematics. For the chemistry, it's hand waving what he does, right? And so to mathematics, my question is, if I want to answer these questions, how slightly more, how complexity, how clear that you reduction or something. If you do it with the same mathematics, you put something with autocatalysis. If you do it with the same, then you have it always. And then it's a question whether the switch over the bifurcation or the switch over the threshold or whatever happens or not happens. And this is a property which does not distinguish the living from the non-living. So you can have the non-living Belousov-Zapezinski, whatever kind of things, the originator, brassolator things, without knowing to talk about a living thing. So you ask for so my question is rather who changes the mathematics. So how can a system all of a sudden become able to do these bifurcations, or to do this? I mean, by how who introduces the autocatalytic parameter, for instance?
But then,
in the equation we put it.
No, we don't put it. Typically in the system there is no autocatalysis, but the autocatalysis is an emergent property of the network.
And who does it?
It's the energy. Typically what, maybe I can show it, typically in this kind of system, can it be seen there? Yeah, okay. Typically in this kind of systems you have all possible, okay. When you input energy, you put the molecule, you force the molecule to perform some cycles of reaction because you input energy. And this is all the possible loops that are inside this kind of system if we limit it to only to the dimers.
But somewhere in all
some of these loops are network autocatalytic.
Exactly. So it is in a way hidden to our eyes, but it's present in the errors. I mean, somehow a normal coordinate or something like this is autocatalytic with a simple mathematics.
Yeah.
But the detailed system does not show it in a simple autocatalytic parameter, but it must have the ability to close. So it must be present before. It cannot arise. It is.
It is that what arises is that if you have just a system, you have a mixture of amino acids and just it. So at the beginning you just have the amino acid, and if you input energy, they're able to polymerize. And then you have some different stability between homopeptides or heteropeptides, etc., etc. But and you have different kinetic parameters, thermodynamic parameters. But just because you input energy, you force them to polymerize, and the polymer are less stable, then you're forcing this. And it's just because of the kinetic and thermodynamic nature of the system, you have input energy, and then you generate autocatalysis just in a natural way.
So when we say emergent, usually we mean we do not know why. Now in this case we say we know why, and it is something like introducing a normal coordinate which has a simple equation where we see autocatalytic, and before we had a funny description where we did not see it, but it was there. Or what
yes, okay.
I mean, what is emergent in the mathematical sense?
Well, I think that what is emergent is that, the problem is always difficult when we introduce the word emergent. Okay, what we have is that as long as you have no energy, you have no activity. When you input activity, you allows the formation of this autocatalytic loop. We can, of course, understand why there are autocatalytic loop on the basis of the respective reactivity of all compounds. But as long as you have this autocatalysis and the fighting mechanism between this autocatalysis, then you can only have a bifurcation, because you can't have the coexistence of the two. And then you have this kind of choice, that is just a stochastic choice, we go right or we go left. And then at this moment, there is the emergence at this point, when you have bifurcation. The system just go in one direction. And when it goes in one direction, maybe there will be other catalysis process, autocatalysis process that can appear. Then this system may have other possibilities of bifurcation and then go further, etc., etc.
I mean, my question is, if I simplify it, say some Landau, Ginzburg kind of, I have a potential or something.
Yes.
Then of course you can have a potential which allows for instability, and then you can not ask about this potential, but you ask, okay, I start somewhere, and then I give it energy or something, and then I have a threshold, and above that crazy things happen. But this is not my question. My question is, where did this potential come from, which allows for that?
You need the source of the energy?
No. I mean, I speak now in a simple mechanical analogy. If I have a potential, if I have energy mountains which allow for instability, because I have saddle points, all kinds of things, and then I can always not ask for the real origin of the instability, namely the shape of this potential, not ask, and instead ask my initial condition. I kick it, I give it some energy, I have a steady state, however I put it. So then I go around in an energy valley, or which I do not understand the reason for, but which is actually, in my mind, the reason for the instability. And then I put the question to the energy which I put in the system. So my prejudice would be that this kinetic system does have inbuilt, from the first equation to the last equation, the potential instability, which we later use. And then we deal with something which is not in the equation, such as an initial condition or
of course,
energy flow or whatever, and we go up to the threshold, we explore this energy mountain, and then we say we have created a proto or whatever something, but I don't think we have created. I think we have already assumed it and played with its parameters.
Yes and no, because of course, from the beginning you have all the everything exists in the whole phase space. It's maybe
I can maybe.
It's if you have this phase space of all possibilities, of course everything exists in this theoretical. It's all the possible realities. It's all the potential states that may exist. Of course everything is there from the beginning, but you not from the beginning, because not is realized. Not all the reality realized. All the possible molecules. Now, if you just look, it's a very common consideration. If you look at the possible sequence of peptides, you can't build all the possible peptides because you have a very huge combination of the possible peptides. But even the peptides that never have been built, they have a theoretical thermodynamic and kinetic parameter. Even if a specific chain of 100 amino acids doesn't exist, it exists in the potentially existing molecules, but it's not existing.
I mean, to put it provocatively, the question, how does life arise, or instability, is now transformed to the other question, how can I prevent life to arise? Because in principle I cannot prevent it.
Yes. Yes, but I think
it's no problem that it arises. It's a problem to make it not arise. I have to keep low with the energy flows or whatever. Is that more or less the answer? So I have a mathematical system where everything is put already. And I only play with the parameters where it does not yet happen.
But those. I understand your question, but how to formulate is that you have the emergence of some parameters at some point, because you start from all the possible theories. You have something in the phase space, and you have only few molecules that are randomly distributed, and you have emergence in the way that as long as you evolve, if you have this self-organization and then you collapse the possible molecules in a very specific phase space of all the possibilities, then you have some kind of choice, it's a choice by bifurcation. And because your system, because of its history, is evolving in one place rather than the others, it will be built on the basis of some molecules and not on the others, and these molecules will have these specific properties, and then it's only these chemical, kinetic parameters or thermodynamic parameters that will be used and not the other one. And so that you have the emergence at this level, even if theoretically everything pre-exists, of course. But the system is just...
to say what I have discussed with Stuart Kaufman, and where I would see the alternative. In a way I say what he does is not touching the crucial question, but making a nice system within which you can play inside mathematics, and you can go to the other side, and from the one side you don't see it, and all of a sudden you see it, and you say here, that's the immersion, that is where it arises. But I give him now, for instance, an example. If you take simple chemistry, protons in water, something very trivial, which play a huge role in life, but you cannot make anything interesting. It's just acid, hydrochloric acid and water. You cannot make a lot of things. But this property changes dramatically the moment you create an interface. So you, by some chance, have something which makes an amphiphilic or whatever interface, and then you have kind of fluctuations, and then the entropy of the interface plays a role. Just something new. Something the phase space of the old system could never have predicted, because it is a different phase space. In the matter, it's like in the mathematics. So you change the equation. So in thermodynamics, you say I deal with no more with the apple. I deal with the pie, and I get different results.
Yeah, but this is fundamentally different.
And then you all of a sudden get things which you could not have before. You have propagating excitations along the surfaces. You have fluctuations where someone who brings in a chemical can have reactions at the surface which would not have happened outside, and he would be forced to call it catalysis and all kinds of nice things. But my main point is, Stuart Kaufmann cannot do it. Because he can talk about the new system, but then he just takes the other phase space and still another. And the critical jump is the change of the phase space, the new possibilities and unthought of possibilities.
Yeah, okay.
That is my discussion with him.
Yeah, okay, I see. But it's roughly what I think that it's roughly what I said when I said that we have change of the topology of the network and change of going from horizontal complexity to vertical complexity, is that we have some kind of complexity, and because we are reducing the system only centered on, for example, amino acids, RNA, nucleotide, etc., we are reducing the representation of the molecule in the existing phase space. But because we are reducing, we have this effect of vertical complexity. That is, of course, yes, we are increasing the phase space. Yes. It can be also told in this way.
I mean, the key point for me is the unthought of possibility, which within an axiomatic mathematics does not exist.
What do you mean by this concept?
Well, if I start with a phase space something, and I make my nonlinear or whatever equations, and I get all these reductions, I have no way in the concept to think of that the phase space is a totally other one. No more in 3 dimensions on the surface of something. It's just another one. Then I can do the same game.
Yeah, but this is just a limitation.
In the axiomatic, the key question to me, how life arises, is really how how do these arise?
But you always can say that. Yeah, but the phase space part of the phase space, you didn't think about it.
Exactly.
Actually, yes, but it was existing before. So is it?
But it may be different. It may be wrong.
Yeah, but okay.
It may be wrong.
Okay, I see your point.
In the whole mathematics.
I mean, Connie asked in the beginning the question: where does the landscape come from? What defines the potential? And if you take your system, your potential is simply defined by the reaction parameters: the value of A, the value of P, the value of alpha, of E, and of H.
Yes.
Right? So once you give those values, your surface is given, and you know already what you have. You have 2 attractors in that case.
Yeah.
And so therefore, the answer to your question is it's given by the choice in this case of the reaction parameters. But of course, this is a simplification. In reality, these reaction parameters do depend on temperature. They depend on pH.
Yes.
They depend on a lot of other relatively simple things still. And so and maybe there's more complex things which could also change those parameters.
They are the consequence. They are not the cause. They are the consequence of something deeper.
But once you start changing these, the landscape is actually changing all the time.
Exactly. I mean, in a way, in our physics, the best thing is we have such a Ginzburg or whatever thing, and we can derive from it. And then we have and this is what usually is not done. Kaufmann does not do that. I mean, if he talks of potentials, they are added somehow as a frame later, but not somehow the foundation. But anyway, I'm just.
I think.
You see this.
Yeah, of course, I see this point,
but it's very difficult because the people who do it, they are experts in mathematics and not in chemistry, so they are not trained. I mean, just like Jim Watson, where we had the discussion, I later asked him, he was as a boy all the time spinning balls. That was for him an important thing, he pointed out. So someone whose mind has been spinning balls all the time and was sure that in space you cannot explain how the tennis ball will run. It's like Maxwell, James Clerk Maxwell had also a kind of ease to go on with spins. Someone like this can have the idea of a helical structure in DNA with an ease which is impossible for others who think in space. And similarly, in this question, so it came from outside of mathematics. And somehow, so with the right hypothesis, I mean, from the premises, all the results depend. And this is the kind of input I would wish to see in the Kaufman's approach. When you start.
But I think this is typically, I think that, well, especially in this analysis of these chemical networks, and if you go to this network community, you have lots of difference between understanding the dynamic of the network or the dynamic in the network. And it's really that, because either you fix the network and you look at what is happening inside, and so as you in the terms you say that you have this phase space, the phase, the shape of the phase space is fixed, and then you see how it's evolving inside, or you try to look what is the feedback that what's happening inside on the network itself, and then you modify the network, and then you changing the shape, etc., etc. But it's right that it's much more difficult to understand than whatever you are doing. There are lots of parameters after that to play with, and but
I mean, there was always a controversy between Stuart Kaufman and Manfred Eigen, who is of course elder and has evolution theory also on kinetics, but not. Manfred Eigen more or less said the last word on this evolution theories, at least the last new word I heard in 1989. He had in the Klassiker, Wissenschaften, put things together and made a preface, and where he said the key problem of evolution is that we do not understand catalysis. And even that doubt cannot be raised in Kaufman's mathematical, self-consistent, whatever, going. So there are deep questions. If one starts these things, it would be very useful if one has still the liberty to go. Stuart Kaufman, I mean, he appeals to many chemists because they are pleased. He uses all their molecules, all their things, and then they admire the mathematics, of course, rightly so, but are not led to their premises in the thing. So if one starts things, it would be not bad to play with the very premises. And
I totally agree.
It's a slave of them, of the thing. I'm not,
actually, it was one of my first purpose when I developed this model, is just all the model that's trying to explain the emergence of homokaryotic. At one point they just say, there is this autocatalytic step.
I mean, if you can do that...
And what I've done was, we need to remove the autocatalytic step and just have inbuilt inside the system.
And if you can convince me of that, I'm just suspicious that you have it somewhere in the mathematics, as long as we do exact mathematics. But if you can convince me that you came from a system which has nowhere in the assumptions...
Well, it's not nowhere in the assumptions.
Catalysis, and then you come to a one, and then you have done a thing.
There are no direct autocatalysis in no place in the system, but you can see where the autocatalysis is indirectly in several steps. It's the point.
You can maybe show this as well.
Maybe it's obsolete.
No, it's fine. It is very easy.
But show you the page 11, I think it was.
No, I don't think that's...
Your cycles, this one, here.
Yes. Okay. Yes, you can see that.
So, for example,
the autocatalysis, for example, is it? If you have the activation of one monomer, the activation coupling of L plus D that gives LD, so this is just polymerization step. Just the epimerization of LD into DD, the L is reversed, and then the hydrolysis of DD into 2D. Roughly, it's an autocatalysis transformation of L into D by D. It's this very simple step actually.
Can you just repeat this?
Yeah, you have activation and polymerization of a L plus a D. That's build you a LD molecule.
Yes.
You have the epimerization, the racemization of one of the amino acid residue inside the chain, so the LD transforms into DD.
But what is that? This is a crucial point. What does LD, how does that become DD, and what does it mean?
But it means that one L is reversing into a D. This is a very...
it's just a topological thing.
Yes, that's called epimerization.
It's epimerization. It's just the amino acid. It's just reversing. It's changing its configuration.
I understand.
Yes, and this is known that actually it's the faster way for amino acid to change their configuration is at the end of the chain. So this is chemically relevant.
So you are reading. I see that one can read this cycle as autocatalysis.
Yes.
I also see that one can read it alternatively as isomerization.
Yeah.
So if I face this cycle,
yeah.
I only go from L to D,
yes.
the horizontal.
Yes.
Then it's a simple isomerization.
Yeah.
But if I now say no, I look at the D which I have added here.
Yeah.
On the down.
Yeah.
And at the end I have one extra D.
Yeah.
Then I have autocatalysis, of course.
Yes.
So that's the key idea. I got it.
Yes. Is that you do not have exactly, you do not really put direct autocatalysis, but you just have some kind of fuzzy autocatalysis.
Catalysis is an apparent.
Yes, it's the catalysis only exists at the moment that you can have all these reactions working together. And it's even more interesting because actually for that you need to pump energy to have this running in one direction and not into the other. And so that's why we really can have the bifurcation. It's more than just a catalysis, because it's just a catalysis of the inversion of reaction. You can only go to racemization. But because it's coupled to the consumption of energy, you can have the bifurcation.
I understand. I mean, there is even... Oh, I understand. Yeah. That may be very true. So, I mean, I play on a little different side, but one could perhaps... use your way to think about it. I think if I think of, say, of a lipid surface, and if it forms vesicles, it has already the dimension of a cell. Leave out complexity later. Now there are certain phospholipases, enzymes or catalytic activities which make within the lipids these lipids.
Yes.
So they become more lipids, but not more cells. So when you want replication, but when you have a surface which has instabilities, if it's too large, and if it's able to divide and become smaller, as you can do in the experiments on occasion, you could have a similar thing that you have no replication of cells. You have only a chemistry which has no idea of replication, but something else comes in, like your isomerization, namely instability, that Laplace, whatever things. I mean, that is. I like this idea. I like this idea that autocatalysis comes in by another viewpoint.
Just to build this in several places. But what we also really always have to take into mind is that all this, you need some irreversibility inside. This is really working because we are pushing the reaction in one direction.
Wow, okay. But this is irreversibility, we can have that, but this will not change.
Okay, I don't know exactly the details of the system.
Because you can always put it to initial conditions. So. I see your point. Thank you.
It's okay.
So, in order to, so first of all, to just repeat the same thing in my words, this reaction which you had here, you have an L and a D, that gives you your LD. and this.
These are the neutral loops that are only dissipating in
the end to give you an error.
Yeah.
Actually, in this case, no,
they take it.
Yes.
No, these are the two autocatalysts.
Yes.
These are the reverse, the bad one, and these are the neutral loops that are only dissipating energy.
Here we have an L and a D that it turns into LD. This epimerizes to the D, dissociates into a D and a D. And so we have in the end a reaction from LD.
I see that. Yes.
So the question then is how to go on from here. So the one thing that may need to be added on is to go to more complex molecules. So for example, we should maybe go into an alphabet where we have at least 4 different letters, if not more. At the moment we have 2 different letters.
Yeah.
And maybe we can have more complex letters, of course, in alphabet, but maybe that's good enough already. And then one can continue playing the game, and one can maybe allow for, and you call it epimerization, but maybe one should just call it mutation.
Yeah, but this will become quite much more difficult.
And there will be mutations which are, of course, depending on the neighbor. So in this case, for example, this can turn into a CC, for example.
Yeah, but this becomes totally non-chemical, and this is the problem.
You think that wouldn't work, yeah?
This is totally non-chemical.
So what are the possibilities? If you once we have this, what can we do? I mean, we can certainly do a mutation, right? So that can.
And how do you want to get autocatalysis? I mean, this kind of.
Yeah, that's the problem. Is as long as you.
Do a network cycle.
No, if you want to get stuck in this kind of framework with amino acids, you won't be able. But I was trying to. Is it possible? When I was studying this kind of. No, maybe you can have some maybe interesting transformations that. Okay, when you have a chain, okay, for example, A, B, C, D. You can have some cyclization. For example, this plus this. And this maybe you can. I think you can easily understand introducing just the reversal of the chain. Maybe there is that.
Reversals, yeah.
Yeah. But reversing the chains.
Can you also have a reversal in here?
No, only the two at the end, mainly. This can be done very easily.
Okay, so in other words, so if you
have not changing.
So if you have a thing like this,
I don't know if it can.
Then you can from this you can generate for example, a B.
Yeah, but it will get out.
For example, also an FE,
yeah? Yes, except it won't work like that. Because actually, if you have a chain, it's the 2 that will be cut out to break the cycle, and then the chain is removed. And this one, okay, 1, 2. It means that yes, you can easily imagine the interchange of the 2 1, and then the chain can start back.
I cannot answer.
No. I think that okay. This is just. I think that you can try to make some complex reactivity. Maybe you can try to. I have to think about it. But introducing the cyclization of these peptides, you can have some interesting transformations of the chain themselves.
Yes, and then one needs to answer your question, of course, how to do a catalysis from this, or what to actually
But maybe it's possible.
One has to generate a diagram. I mean, so you come up with a new set of rules, as you were saying, like for example this rule, and then once you have this rule, you have To answer the question, what are the possible cycles?
Now, the idea will be that we have this, for example, we have these very simple rules. Then we have to think about and find, is it possible to find autocatalytic cycles on this basis of these rules?
Exactly, yes.
At this point, if it's possible and we find that, then we just launch a simulation. It's very simple, and because we know that there are theoretically possible autocatalytic cycles in this, or these autocatalytic cycles sufficient to observe the bifurcation, if it's possible on the basis of very simple rules. And then this is some kind of emergence or self-organization or whatever. Yes. But first, we have to just to think about, is it possible, at least theoretically?
There must be a huge literature on that. I mean, people have been thinking about these things.
Yeah, I think so, yeah.
But I don't...
I should think about it. Maybe there's something there. I have just to play with this and see if it's possible. Or maybe it's not possible. But yes. Actually, so the very general idea there is really to build these chemical systems on the basis of the most simple possible reactivity. But knowing that even with this very simple reactivity, it's possible to build this kind of autocatalysis and then simulate to see if it's sufficient to have some attractors and bifurcations.
Thank you very much.
Thank you.
Interesting. Actually, we had yesterday a very similar discussion in the Karolinska about this life, but more from the molecular. Okay, I see you. And this is a paper of Charles Bennett you were.
Yes.